when I do this, I can't see him. It's 1, 2, 3, 4. I only see 5. Okay, maybe I should do that. Oh, okay, now I can see him.
Welcome to a real highlight of this year's machine learning summer school. Yoshua Bengio is a professor in the computer science and operations research department at the University of Montreal. He's a founder and scientific director of the Mila Institute and of IVADO. He's also one of the directors of the CFAR program on learning in machines and brains. I first met him at AT&T Bell Labs when I was still a student, but it's really at the CFAR program where I got to know him as a scientist. And the CFAR program is also a central inspiration for the ELIS initiative, which many of us are now trying to push in Europe. Joshua is a fellow of the Royal Society of London and of the Royal Society of Canada. He has received a Canada Research Chair, a Canada CFAR AI Chair, and he's a recipient of the 2018 Turing Award for pioneering deep learning. He's an officer of the Order of Canada. He's a member of the NeurIPS Advisory Board and co-founder and member of the board of the ICLR conference. His goal is to contribute to uncovering the principles giving rise to intelligence through learning, as well as to drive the development of AI for the benefit of all. We're looking forward, Joshua.
Thanks a lot. Let me share my screen here. Do you see the slides?
Yes.
All right. So I'm going to tell you about deep learning for AI, meaning with a perspective towards our progress in understanding human intelligence and building intelligent machines. And I'm going to start with what got me into this field in the first place when I was a master's student. And I started reading neural net papers in the mid-'80s. And it's the theory or the assumption that there are a few simple principles that can give rise to intelligence, whether it's in humans, animals, or machines, and that these principles revolve around learning. And that those principles would be simple enough that you can compare them to the laws of physics. In other words, that intelligence is not just a huge bag of tricks and pieces of knowledge, which was the dominant thinking in the 80s and 90s in AI, but instead the result of general mechanisms to acquire knowledge. All right. So that's really what motivated the departure from classical AI into machine learning that I contributed to starting in the 80s and then 90s and then this century, where the knowledge is not completely provided by a human, but it's mostly provided by data. And that has really worked quite well, as you know, and that's why you are in this summer school. Now, the neural net approach to AI is specific in that among all the ways that we could imagine allowing a machine to learn, we are considering how animals and humans do it with their brains. And there are a few principles that you find in pretty much all of the neural net approaches, and especially those that have been successful in this century, which we usually call deep learning. So first of all, computation is the result of the combination and the synergy of a large number of very simple adaptive computational units. So that's basically what neural nets are about. In addition, the form of computation done in these units is inspired by the form of computation we find in neurons in the brain, although there's still a lot that we don't completely understand there. And so there are many variations of neural nets. Now, the thing that really got me excited about neural nets in the 80s and has been throughout my career a source of great inspiration and success is the idea of distributed representations. In other words, what we're going to learn is not just a function, but we're going to learn intermediate representations. And those representations are not symbolic. They represent potentially symbols or other concepts through the simultaneous patterns of activities of these neuron-like elements. And so that is something that looks very simple, but actually has very deep consequences in terms of generalization. My own contribution to this has been in the realm of natural language with learning word representations in neural nets around 2000, and then extending this for machine translation 15 years later with the use of attention, which I'll come back to later. Something that you find in the neural net approach, but also in many other machine learning approaches, is to think of how intelligence arises in humans or animals as combining three things, essentially. What it is that you're trying to learn, an objective or reward function, then how you learn it, how you optimize that objective. So that's sometimes called a learning rule in biology. And then the sort of family of functions in neural nets you talk about architectures and parameterizations. And then there's this general idea that was not obvious in the 80s, that we can have a big complicated machine and learn all of the parts together with respect to this one objective. So this is what we now call end-to-end learning. And that idea has been extremely successful, although it's also interesting to question it when the size of the system becomes too large, and we may want to use some approximations of this principle. All right, now let's talk a little bit about the statistical problem of learning, which I think neural nets help us with. And that is what's called the curse of dimensionality. And I've spent a lot of time in the 90s and 2000s thinking about this. In the simplest ways that we can learn to generalize to new configurations of the data, we take the information we have acquired in some configurations, and we're trying to guess what other configurations, values of the function we're trying to learn should be. And in one dimension or two dimensions or three dimensions, it's actually working quite well to just assume some sort of smoothness for the function you want to learn. And so if I already know the answer because I have an example at some configuration, I can guess that in the neighborhood of this example, this will still be a fairly good answer, and maybe I need to interpolate between nearby examples. And that works incredibly well in low dimension, but it breaks down in high dimensions because there are just too many places to consider, and you end up requiring an exponential number of examples with respect to the number of dimensions in order to do a good job, unless the data lives on a lower dimensional manifold, which is also something that's been explored, but it's not always low enough. So the trick now is, so one way to think about it, and maybe it's a general theme of the way that I'm thinking about machine learning, is this smoothness assumption, which we're using in like non-parametric machine learning, is a prior. It's an assumption, right? It's assuming that the function we want to learn is smooth, and that's great. It's very powerful, but maybe it's just not enough. Like maybe we need to add more assumptions. And in a way, what I'm going to tell you is that the main trick that makes neural nets work, this learning of intermediate representations, is going to add more assumptions. And it's because we're bringing these additional assumptions that we're getting additional generalization. Of course, it only works because the world in which we want to apply these machine learning methods somehow is compatible with those assumptions, or at least, for a large enough part of it. Or even more specifically, with my perspective on AI, it's going to be good enough to build intelligent machines which are as good as humans. Now, humans are not like perfect learning machines. There are things about the world that we're not good at learning, and there are things about the world that we are good at learning. So if we just focus on the assumptions that humans make about the world, and build machines that exploit these assumptions, then we might reach more easily the level of intelligence of humans, which is already a pretty amazing goal. Okay, so how are we gonna bypass the curse of dimensionality to some extent? We're gonna add extra assumptions about compositionality. This is really the most powerful concept in computer science in general, but it turns out it's an incredibly powerful concept in machine learning as well. So you already have noticed that human language exploits compositionality. And the question is, what about machine learning, right? What I'm going to try to tell you about is, in the first part of my presentation today, is in the standard neural nets and deep nets, there's already two forms of compositionality that we are exploiting. And then tomorrow I'll tell you about another form, which is closer to the one we use in language. So the first two forms are one derived from the use of distributed representations, and the other derived from the fact that we're going to have multiple layers of these networks. So why do we have compositionality in distributed representations? I'm going to elaborate, but basically each feature, each neuron in each artificial neuron in a representation can be, say, on or off, or can take different values. And you can see that this is very rich because now you've got an exponential number of things you can express. But at the same time, you can learn each of these things kind of separately from each other. And so you can generalize to new configurations you've never seen. So that's a form of compositionality in the feature space, because you're learning features. You're not just taking features from the input, you're learning new features. And then the second form of compositionality is one which is closer to the usual meaning of composition of functions, right? So instead of having just one, doing things in one go, we think of it as learning representations on top of representations on top of representations. So we are composing functions and building gradually more abstract and complex features. That's another form of compositionality. And for both cases, we can prove things mathematically about the potential exponential gain in terms of expressive power that you get. Now, of course, you have to realize these are going to be assuming things about the world. And that's true of any prior. So it's not guaranteed that the things we want to model are going to be easy to model using these assumptions. But it turns out, and this is something we couldn't guess before, that it works really well, as we've seen in this century. And probably the reason is, as I said before, is that humans exploit that. And so tasks on which humans are good tend to be tasks on which neural nets are good, at least for some of the tasks that is true. And there are still tasks that we have some work to do. Okay, so let me try to go a little bit deeper about this concept of compositionality and why you get a kind of exponential advantage in terms of generalization. So let's consider a very simple 2D space, right? We're going to have examples, and the way we're going to build our learned function is going to, in a way, partition the input space into regions, and in each region we're going to output something, some value. So a simple way to do it, which seems to make a lot of sense, is the classical local non-parametric approach, which I labeled here not distributed, where we might take each example or each cluster center and create some sort of Voronoi diagram of some partition, where we say that the inputs that are in the region around each example are going to be associated with the label that we get for that prototype example. That's simple enough, and it's very, very flexible, and you can learn pretty much any kind of function if you have enough points. But you can see that if you go in high dimensions, the number of regions that you would like to get is going to grow exponentially in order to cover all the variations you'd like. And thus the number of examples you would need as well. Now let's consider another way of doing this, because you might say, well, there is no choice. What else could we do, right? Well, we can add assumptions. So here's one way to think about it, and that's on the right. That's the distributed approach. We're going to learn intermediate features. And here, just to make it simple, we have 3 features. So each of these features is going to be a linear classifier. So what is a linear classifier? It takes the input space and splits it into parts. And here you can see the 3 colored lines. Well, each create a partition. And so there are like 2 regions that they can understand, each of them, where the output is 1 or where the output is 0 for this linear classifier. All right, now let's consider the set of regions that all of the features together define. Well, you can see you have all of the intersections of these half planes. And if you have high enough input dimensions of roughly the same amount as the number of features, then you can get an exponential number of regions in this way. So why is that useful? Well, let's say that you've seen examples for some of the regions, but not all of the regions. So so you might think with the approach on the left that for the regions where you have no data, you're screwed. But with the approach on the right, what happens is to learn the sort of meaning of the blue partition, I just need to have examples on both sides. And then similarly, for learning the meaning of the red one, I just need examples on both sides. And even though I don't have examples for all of the regions, I have enough examples to learn each of these features. And now I can generalize, of course, to regions that I don't have any data, but why would it work? It works because those features are meaningful. They actually describe something about the world, which somehow could be learned without having to go through all the possible configurations of the input. And in fact, it works, right? So to make it more concrete, here's an example. Think about a ConvNet, which is the kind of neural net used for images that everybody knows about. And let's say you have these images, and just focus on images of people. And let's say that at some level in the representation, we were lucky and we learned those features that capture semantically meaningful aspects of the input image. For example, if the inputs are people, maybe there's going to be a feature that's going to figure out that an important aspect of the input when we're talking about people is whether or not the person wears glasses. And maybe there's going to be another feature that's going to figure out whether the person is a female or a male. And maybe there's going to be another feature that's going to learn whether the person is a child or not. Okay, so now you see the whole point is that it's plausible that you can learn about detecting whether a person wears glasses or not in a way that's independent of the other features. Like, whether you're a male or female, if you have glasses, you have glasses, right? They may look a bit different, but still your glass detector should work. And so, so now you can see that the number of examples you need to cover all the configurations of these binary features is linear in the number of features, but the number of generalizations you can get correct is exponential. So that's the idea. That's basically why deep learning works. Now you could say, well, how do we know that the neural net is going to actually learn these semantically meaningful features? Well, we don't, and so we do experiments, and people have done that. So that's a paper from already a few years ago, which tried to put a name on the hidden units that were learned in a ConvNet by looking at which part of the input unit was sensitive to, and then looking at, like, for example, there's a unit that seems to like tables, right? So if you look at the images, the parts that it's sensitive to, there is, and then you ask a human, would you give a name to that set of things? And they would say, yeah, this guy is detecting tables. And you can do that for a bunch of units. And you find that near the top level, like the top hidden layer or the one just before, you do find those features that humans could put a name to. And those names are not the same as the classes that it was trained on. So it just, in order to here recognize places, it did invent those features that happen to be semantically meaningful in the sense that humans would put a name on. So it works. All right, so to summarize, what we're talking about here, that's the main property of deep learning, is we're learning these internal representations. So this is different from linear models because there is no intermediate representations. And this is different from other machine learning models where the representation is fixed. Like a kernel actually gives you an intermediate representation, but usually the corresponding feature space is fixed by the choice of the kernel, and maybe it has a few parameters, but you don't learn a complex representation from there. And then once you think a bit about it, an important question is, okay, so if we're going to learn these representations, how should we do that? Like, what is a good representation? This is an open question, obviously. We can do it in the simple supervised way that I said, in which we say, well, whatever is going to help me solve my supervised learning task is good. And in general, you could say that a good representation is one that makes other tasks easier. And so I'll come back to that. Like, you can hope that there is a generic representation, especially if you think about the way humans have high-level semantic representations. You can hope that there's a high-level representations of the world, similar to what humans have in their head, that is good for a large diversity of tasks. Basically, it's good to understand how the world works, understand causality, all of these things we'd like machine learning to capture. And so in the evolution of deep learning from earlier AI approaches, I think it's interesting to see how it went in the from the 80s and then 90s and 2000s and to gradually deeper systems. So initial AI systems, when I did my grad studies, there was no machine learning taught in grad school. We were learning about classical rule-based systems, and essentially a rule-based system is a hand-designed program that maps inputs to outputs. Then there's been, of course, a lot of work on linear systems where you do a lot of hand design of the good features, and a lot of the computer vision and starting from the 60s up to when deep learning really kicked off in this century was done like this. And then if you consider the standard MLP with a single hidden layer, you just learn not just the output linear classifier, but you also learn those features. But those features themselves are just like linear classifiers. And then basically you can say, well, those features themselves, maybe they should be the composition of more computations, and so you make it deeper. And what's interesting is that when you look at what those hidden units learn, you can see as you go higher up in these, especially the convets which learn about images, it's easier to visualize. And you can see that as you go higher up, they do learn features that are meaningful. At least they seem to do something that we can understand and become gradually more complex and object-like as you go higher up. And of course, the way that humans also make sense of the world has this tends to have this hierarchy, both in terms of what we find in neuroscience, looking at the hierarchy of features in the brain, whether it's for images or for language, or the way that engineers build systems usually have a hierarchy of concepts. And so, yeah, so we can create these architectures with low-level features, mid-level features, high-level features, and then a trainable linear classifier on top, and train the whole thing together. So as I mentioned, there's been many theoretical analysis of deep nets, and I have not kept track in the last few years. But one of the things in the early days of deep learning, about 15 years ago, one of the things I was trying to do is convince people that deep learning had theoretical advantages. And so we embarked on this journey to try to do that. And the maybe most powerful output of this work, which took about 10 years to complete, is this NIPS 2014 paper, where we see that with piecewise linear units, you can consider the expressiveness of the network in terms of the number of different pieces that a particular piecewise linear function is going to have as a function of, so, if it has many pieces and you wanted to approximate this with a classical non-parametric method, like a piecewise linear approximator, then you would need as many examples as there are knots, right? And so, so the interesting question is, can we do that with less examples, or at least less parameters? And the answer is yes. And how many pieces do we get for, as you vary the depth and width? Basically, you get an exponential advantage in both the width and the depth of those networks. So the L here in this formula is the depth, and the N here is the width, and N0 is the input dimension, and this is the number of pieces. Okay, so this is nice. Now let me kind of step back a little bit, and why are we doing all this? What is it we're trying to achieve at the highest level of representation? And I'll come back to that mostly in the second part of this talk. We're trying to learn these representations, and what we would hope for, as I try to explain in my examples, is that the highest levels of representation capture the kind of high-level abstractions that humans seem to use to make sense of the world. And these might be like causal explanations. They might be the kinds of concepts we manipulate with language. And what's interesting to think about from a geometric perspective is that these concepts, these high-level variables, are hidden in the data, right? So if you start from pixels, it's very difficult to go from pixels to high-level concepts like the presence of objects and where they are. It's a very nonlinear function. And it's like if the simple abstract concepts that we use to make sense of the world have been mixed up in a complicated way, entangled to give us the pixels. And so the job of deep learning is really to disentangle that mess in order to recover those high-level concepts. And if we can do that, it's going to make generalization much easier. Why? Because once you have reduced this like millions of pixels into a few relevant abstract concepts, like the boy is throwing the ball, there's just a few concepts that are relevant, and you can generalize easily from this sort of low-dimensional space. And you don't need a lot of data to generalize to a new task from that space. Okay, now let's go a little bit technical. I'm going to share my slides later, and so I'm for sure going to go too quickly for people who haven't already seen these things. And yeah, so a lot of that material is also in the deep learning book, which is available online for free, or you can buy it from Amazon, MIT Press. So just bear with me. I'm going to try to focus on the crucial insights and not spend time on algebra and stuff. Okay, so first of all, these hidden units that I've talked about, I haven't really explained in more detail what they look like. The standard simple ones are just a fine transformation of their input, which might be the raw inputs or it might be the outputs of other units, followed by some nonlinearity. All right, and we call that nonlinearity an activation function. So here it's the G, and notice that it's not linear; it's affine, and this this offset or bias is something important. Okay, so for example, you could use one of those units as a logistic regression if we use the sigmoid as the nonlinearity. And so you can think, as in my example with the partition, that what each of the features is doing, each of the hidden units is learning a little binary classifier with a soft output to tell you how far you are from the decision surface. We can take those features as inputs to another linear classifier that's going to produce our output for whatever task we want. And we could do, of course, more layers, and that's going to allow us to have more complex and interesting functions. And there's also a lot of theoretical result. some dating back to the late 80s, showing that you can, if you have enough units, you can represent any continuous function, smooth continuous function, to some arbitrary degree of precision. And what we didn't understand until recently is that why would you need deeper networks? So even a neural net with a single hidden layer is a universal approximator, just like any non-parametric approach. If you increase the number of units, it's like you increase the number of parameters, you can fit any function that's reasonable. So that's cool. Of course, these early results don't tell us whether it's going to be easy to find the parameters. So there's an optimization problem. It doesn't tell us whether we're going to get good generalization. So there's a lot of theoretical work and practical work on both of these questions, which I won't have a lot of time to talk about. But of course, the bottom line is it has worked really well for a number of applications. Regarding the depth, well, I already mentioned some results suggesting why you would have an advantage. So even though you could represent any function using a shallow neural net with a single layer, you might need an exponentially larger one to represent the same function compared to a deep net. So that's what we hope to get, basically more efficient representations. Yeah, so why do we need a nonlinearity in the middle? Well, if you didn't, then the whole thing would be linear, because the composition of linear operators is a linear operator. And you would lose the universal approximation property. Yeah, and there are many types of nonlinearities you could use. These days, people use rectifying nonlinearity like ReLU and some variations of them. And for the output, depending on what you want, then you might choose different kind of nonlinearity. If you want to do classification, typically you'll use sigmoid for 2 classes and a softmax for more classes. Oh yeah. In 2011, we had a quite interesting result, which I don't think we understand yet theoretically. And what we found was that these rectifying nonlinearity, which had been around for decades, right? They had been proposed as models of how neurons in the brains process the kind of nonlinearity that they're doing. But really, nobody had tried to use them in a neural net on the kind of scale that we could do there. And it turned out that those networks with rectifying nonlinearity were much easier to train than those using sigmoids or tanh. And so I think that's still an open problem why, but since then it's been the standard essentially. Yeah, so you can see on the top left a sigmoid activation, on the right hyperbolic tangent, which is the same up to some scalings and shifting. The softmax is a normalized exponential, which is good when you want the outputs to sum to 1 and be positive, and rectified linear activation is on the bottom right. And then how do we train this? Well, that's interesting because from the very early days of neural nets, it was proposed to use stochastic gradient descent, maybe under different names, but which is, the most brain dead optimization method you could think of, but surprisingly works incredibly well. In modern days, we use a variant of it, which looks at a batch of example at a time. That's mini batch SGD, because we have parallel computing with GPUs, but otherwise it's the same thing. And if we didn't have parallel computing, SGD with a single example in the batch is actually usually working better, especially in terms of generalization than larger batches. So yeah, so we take an example or a batch of examples, we compute the gradient, and we do one step in that direction with a fixed coefficient, which we call a learning rate. And you might want to play with the learning rate during training. There are different tricks to do that, but that's the idea. Okay, so now backprop. Really what we'd like to do is to reduce the error that the network is making. And if we were going to make a very small change, then the direction which gives you the largest change locally is the direction of the gradient, the partial derivative of the output loss with respect to the parameters. Now, that's the best local direction to move. It's not necessarily the best one globally. Like in order to get to the minimum, a local minimum or a global minimum, you might want to choose a different direction. But if you don't know where the minimum is and you want to just decrease the loss as fast as possible, then the gradient direction is the right one. And now the interesting question is, how are you going to compute that gradient? I mean, if you use PyTorch or something, you just press a button, it does it for you. But when I was a grad student, we had to write our own gradient computation code. And it's very insightful to do that. I encourage you to do it. If you didn't have a machine that computes the gradient for you, you could compute it by some variation on finite differences, where you perturb one of the parameters, you measure the loss, and you take the difference between the two losses, perturbed and not perturbed. That's going to give you an estimator of the gradient. Unfortunately, these kinds of methods, of which there are many variations, would require order of n squared computation. So if n is the number of parameters, and let's say to compute my function, I need order of n computation, like I have to visit each parameter at least once, so that's it. I've computed order of n computation at least. And I want to do this for each parameter, this perturbation, so that costs n squared. So if n is 1,000,000, n squared is 1,000,000 times 1,000,000. That's a lot of computation. But if you use backprop, you can do it in order of n. And there's no way to make it faster because you have to visit each parameter at least once, right? So backprop is kind of optimal among all the ways that you can compute gradients, at least in complexity theory point of view. Okay, so the word backprop is not the same thing as gradient descent. Please use the word gradient descent for gradient descent. And backprop is about how we compute the gradients efficiently. And backprop is not supervised learning. Backprop is how we compute the gradients. We can compute the gradients of any objective function. And so it's not just, it could be used for unsupervised learning, reinforcement learning, and so on. All right, just to get the terminology right. All right, so how does backprop compute those gradients? Well, it exploits the good old chain rule that we are supposedly all learned in the early years of our training, and applied in smart ways. So what is the chain rule? We have a composition of two functions, f and g, and we're going to compute the partial derivative of the output of the last function given the input of the first function by just multiplying the two partial derivatives through each of the two functions. So that's the chain rule. We have a chain of computations. X goes to y, goes to z. We take the partial derivatives on this edge and the partial derivative on this edge. We multiply them, and we get the answer. And why does it work? Well, you can do very simple math to see that it makes sense. So a variation in z, if you want to express it as a variation with respect to x, like if I perturb x by delta x, this will translate into a perturbation of y, delta y, by taking the delta x, and because delta x is small and you apply Taylor's approximation, you get dy dx times delta x. And similarly, the perturbation delta y is going to be converted into a perturbation delta z by taking the delta y and multiplying by dz dy. So now if you take these two equations and you plug one into the other, you see that the perturbation delta x turns into a delta z by multiplying the perturbation delta x by dz dy times dy dx. And now if you take the limit of these deltas to 0, you find the partial derivative and chain rule. All right. So that's it. It's really simple. And you can do similar math to see what happens if you have two paths from x to z, right? You can, x influences y1 and it influences y2. And now you get this rule where you're going to add the partial derivatives along each path, and along each path you multiply, and then you add across paths. So that's good if you have only a few paths. What if you have an exponential number of paths? Or actually here it's not So sorry, this is not yet exponential. So here you have like a reasonable number of paths, but now it's not 2, it's n, same formula, we just add up, okay? This gives us, by the way, gives us a very interesting formula, right? So if we have some downstream function z of x, and that downstream function can be expressed through n intermediate quantities, y1 to yn, then the partial derivative can be written as this sum over all of the intermediate quantities of dz dyi, that's the ith intermediate quantity, times dyi dx. So remember this because we're going to reuse it. Now we're going to reuse it in the more general case where the number of paths is exponential. And that's where backprop becomes powerful, right? Because if you were to try to compute this using the principles I explained before, you might say, well, okay, I'm going to sum over all the paths. There's an exponential number of paths, so I have to do an exponential number of computations. The good news is there's a way to do this, which is a form of dynamic programming that allows to do it efficiently in order of n, where n is the number of edges or nodes, whichever. So we're going to reuse this formula, but we're going to reuse it recursively. So how do we do that? Well, for each intermediate node, we're going to make sure we have already computed the partial derivative of its successors in the graph. So here, the y1 to yn are the successors of x. X is the node for which we want to compute the partial derivative, dz dx. If we have already computed dz dyi, then we can apply the same formula and just ignore the details of how each y is influencing z, because we have already computed that partial derivative. And so now we have a simple way of computing dz dx, given that we have already computed dz dyi for all the y's that are the immediate successors of x. We have to be careful in this calculation that we don't overcount things. And so we have to make sure the y's are just the immediate successors in the graph, right? And so in the what's called forward propagation phase, we're going to go from the input to the output, go through each node in some order. So there's a topological sort here. We visit things so that when we visit a node, we make sure that we have already visited all its predecessors. And then we're going to visit the nodes in the opposite order. That's the backprop phase. We initialize the output gradient to 1 because dz is 1. And then we can just apply this recursion. We go through all of the predecessors of the final node. And for each of them, we apply the same recursive rule. And then we go to their predecessors and so on. I mean, basically, we go through this topological sort order, but backwards. And we get the answer for each node, which gives us all the information we need. Either we want derivatives with respect to the input or to parameters, which are like special nodes that don't have any ancestors. Okay, so that's the backprop. And you don't have to apply just on the multi-layer net. You can apply it to any kind of computation that is differentiable or almost always differentiable. So you can have a chain like this, which is what you have in a recurrent net when you unfold it in time, where there's like a hidden layer at each time step, which depends on the hidden layer at the previous time step and the current input. That's the figure on the top. Or you can have more complicated structures that are unfolded based on the structure of the input, like those trees. And today, people use many other architectures, such as transformers and graph neural nets and so on. Now, writing the code for this is still painful. You can make mistakes. And so it turns out that the recipe I told you can be implemented by symbolic computation, and then can be done in a way that does not make any mistake ever if you make sure that each of the building blocks is correct. And so you get a compositional advantage. And we started doing this in a symbolic form with a package called Theano in the 2000s, which then gave rise to other more recent packages developed mostly by companies, TensorFlow by Google and PyTorch by Facebook, which are the methods that people usually use to do automatic differentiation these days in machine learning. What kind of objective functions do we want to use for training these guys? So there are many options, and the most common ones are just to stick to the usual ways of doing things in statistics, where we want to fit the data by maximizing the log likelihood of the parameters with respect to the data. So we want to change the parameters so that the probability of the data is maximized. And in the case of supervised learning, that would mean that we want to maximize the probability of producing the correct output given the input. And so if we have a probabilistic representation, like a parametric representation of the output, maybe it's a class, so we can use a multinullity distribution, or maybe it's a real number and maybe it's Gaussian, or whatever density or distribution we choose on the output. These are going to be conditional distributions. Taking the negative log of that gives us something we can minimize. And this is the typical way it's done. In the case of classification, we get what's now called cross entropy, but it's just a negative log likelihood over a categorical distribution. Okay, so that's the general picture. If you want to learn a conditional probability distribution, P of y given x, the way you do it is you have a neural net f theta that takes x as input and outputs the parameters omega of some parametric distribution for y. Now it's conditional. It's a conditional distribution because omega is going to be different for every x. Now the parametric distribution of P of y given omega is something you know, like a Gaussian. So we have a formula for that, right? So omega could be the mean and the variance. If you do that for the Gaussian, you get something like mean squared error plus log sigma. If you don't care about learning sigma, then you just get mean squared error. If you do it for the multinullity categorical distribution, then you get the cross entropy objective function that I talked about. Okay. What if you have more than one output random variable? Well, in principle, you can do the same thing, but now you have to parameterize the joint distribution between those variables. That may be difficult. In many cases, what we do is we assume that those variables are conditionally independent given the input, and in which case you just end up adding the loss for each of those variables separately. If you really want to capture the joint, then you have to do something more complicated. And I guess I'm not really covering that in these lectures, but there are neural nets that can capture the joint distribution. Mostly these have been designed for unsupervised learning. And you can use any of these guys. For example, the most common one is the autoregressive approach, where you predict the ith variable given all the ones before from 1 to I minus 1. So it's like if you have a parametric distribution for the ith variable, but as input to that parametric distribution, you have like a piece of neural net, which takes not just x, but also the observed value of the otherwise as input. So that you can then learn a full joint. But there are other methods as well. Okay. I don't know if there are questions up to now. Might be a good time if there are.
So far, there are no questions in the Q&A. I don't know if someone wants to ask something.
Or maybe I'm just speaking too fast. And
yeah, I guess we can continue maybe and ask you at the end if.
Yeah.
May I ask a quick question, maybe?
Yeah.
So can can you comment a bit on the? So you said that we have this powerful hierarchical structure.
Yes.
But still, for different applications, we still have to choose the right architecture, right? So can you comment a bit?
Yeah. There's no set recipe. Let's say the practical way of doing it is consider similar problems that people have been using deep learning for and look at what architectures have worked well, and then start from them, see what you get and see where it fails, and potentially trying to understand what works and what doesn't work, and then try variations, right? This is the way that you would typically do it. Like there is no black box recipe to do it. I mean, there is, but it's very expensive. So you can search in the space of architectures, and there's some work doing that, but it takes a lot of compute, because essentially what you're doing is automating what a human would do by trying a lot of different architectures, variations according to some distribution of architectures that you can think of, and then using evolutionary methods or RL to search in that space. And you could imagine that this is how evolution figured out the architecture in our brain, right? Evolution had access to huge amounts of computation, if you put it in computational terms, and the typical grad student doesn't. But if you're working for a large company that has infinite compute power, then you can do these things. But the way that's much more efficient is to use your brain. But it takes years of training, or at least 1 year, I'd say, of playing with these architectures to start getting a feeling for what works and what doesn't work. And of course, reading the literature on because there's now several decades of experience that's been accumulated in the literature. You can also ask somebody who has more experience, right? This works well if you are in a group with other people who have experience, and they can give you hints. But yeah, it's a tough question. I think the better way of answering that is to try to understand what are the properties of the data that sort of match well with properties of architectures. And in the second part of my presentation tomorrow, I'll be focusing more on these kinds of questions.
Thank you.
Well, actually, here is an example. What I mentioned earlier, the work I did on learning representations for words in natural language. And we used a fairly straightforward MLP, except for a little twist. Okay, so first of all, we used something that was not new, that is to model the joint distribution over a sequence of words. We use the same autoregressive tricks that I mentioned earlier. In other words, we predict the next word given all the previous ones. In the experiments that we did in that paper, we truncated the context to a fixed number of words in the context. And so we take the last n words and we predict the distribution of the next one. Now, the distribution of the next one is tough call, because you may have like 100,000 possible words. So you need a neural net with 100,000 outputs. And I guess the reason it hadn't been done before that paper is mostly because it's computationally expensive to have 100,000 outputs. But once you get over that, it works quite well. The other trick was thinking about the input, like how do you represent those words? And so the idea is now to use a shared matrix, which you can think of now we call it the word embedding matrix. So each column or row of that matrix contains a vector for each word. And independent of the position of the word, we're going to use the same word embedding. And here the prior knowledge is that the meaning of a word doesn't depend on its position in the sentence. Right? Of course, it does depend on the meaning of the other words in the sentence, but it doesn't depend on the actual integer positions. And so we should reuse the same parameters for every position. So that's it. And that worked really well. And then a few years later, people experimented with recurrent nets instead of these fixed size input networks. And then attention-based models came, and then transformers, but that's how it started. And when we looked at the words that were trained and their representations projected in 2D, we find that there were like clusters of words that had similar word embeddings and also had similar meanings. And that was very encouraging. Like, see those countries, they're all close to each other, and so on. And different verbs, different conjugations of the same verbs, and so on. So that was reassuring. There were also a lot of papers to try to analyze those embeddings to see if there was some structure in them. And indeed, there's a lot of interesting structure in them. Now, once you start thinking about these word embeddings as representations for words, you can also think of them as representations for phrases, like in search engine queries. And a really interesting piece of work that came a few years after our work on word embeddings was the work at Google, led by my brother Sami, where we consider images and words or phrases in the same representation space, right? So what does that mean? That means we're going to learn two functions, one that maps words to a vector, that's just a table, and another that's mapping an image to a vector. That's like the first few layers of a convnet. All right, and then we're going to have a training objective that's going to make those representations match. So if somebody typed dolphin and then clicked on the image of the dolphin, then you'd like the representations for both the image and the word to be close to each other. And you'd like otherwise those representations to be far from each other. So that kind of idea has worked really well. And a lot of multimodal neural net architectures are in the same spirit. Of course, this was 10 years ago, and there's been a lot of work since then, but that I think was a great idea. You can generalize this kind of story by thinking about different spaces, like here it's X and Y, and then learning a representation for each space. So now we're going to keep the representation separate. So now you can think of, maybe you have a representation for sentences in the Y space, and I have a representation for images in the X space. And maybe you don't want those representations to be the same, because that is a very strong assumption. But what you would like is that there be a mapping between those representations. So for example, if X is images, you'd like to be able to map an image to a sentence. But you don't want to do it in pixel space. You want to do it in that abstract space. And the mapping could be two ways. So, we could go from a representation of a sentence, which is now some vector, to a representation of an image, and then have a decoder that goes back into image space to produce an image, right? So once you understand this sort of representation space idea, you can extend it to connect different modalities. And so instead of mapping them to the same space, you want them to have their own representation, but then have the ability to learn the relationships between those representations so that you can predict one from the other. So that's another way to think about it. And you can exploit this to get even what's called zero-shot generalization. So this is a very early paper, IEEE 2008 with Hugo La Rochelle, where because you have this kind of structure, you can now generalize to, say, a word that you have never seen before in conjunction with an image. But because you have learned an embedding for that word in the context of sentences, so if you've seen the word cat, but you haven't seen the word kitten with an image, but you've seen cat and kitten in texts. So now you've got a representation for both cat and kitten. And so you can generalize to images of cats, to images of kitten in a reasonable way. It's not going to be perfect because you haven't seen it, but it's going to do something sensible. And so you get zero-shot generalization. More generally, you can think of multiple tasks with each having their own representation in the output space, right? So if you want to map an input to many different kind of tasks, you can share low levels of representation and then have a different mapping depending on the task to extract the features that are relevant to that task. And again, one of the early work is from the 2000s, Kulober and Weston, and our own work a bit later. One way to think about it in terms of priors, because I like to think about it this way, is that those tasks have something in common. And what they have in common, I mean, if they had nothing in common, this kind of architecture would be useless. And so what we're saying is that what they have in common is a set of explanatory factors that are represented in this middle shared layer, the top shared layer, right? So maybe for each task, there's a subset of those features that is relevant. And it's a different subset for each task. And in this way, we can get statistical power by having the tasks share, whatever subset of features that they have in common. And you don't have to decide ahead of time what is that subset. It's going to be learning that automatically. You can do that in the input as well. So maybe some of the inputs on different data sets have the same meaning. So let's say I have two learning tasks. One here is predict the joint distribution between person, URLs, and events, and the other is predict the joint distribution between URLs, words, and history of on the web. Now we see that the URL variable is shared across these two tasks. So how could we take advantage of that? Well, we could have a pre-processing kind of representation subnetwork that maps the URL to some vector, and we could share that across those two tasks. Right? So there are many ways you can share. Once you understand the principle of sharing representations, it could be in the input, it can be in the output, it can be in the way that you relate different modalities together. This is very powerful. Okay, so let me say a few words about optimization. One of the reasons why in the 90s neural nets were dropped was that people thought that training them would be too difficult because there could be an exponential number of local minima in the optimization. And indeed, it was proven that there were an exponential number of local minima in some specific cases. That was proven as early as the late 80s. And then because kernel machines came in the 90s and they could learn nonlinear functions and the optimization problem was convex, people essentially dropped neural nets in favor of kernel machines. And in the 2000s, what happened is we started thinking, well, but wait, when we train them like practically with SGD, and we repeat like from different initial conditions, we don't find the same exact function, but we find functions that tend to work as well. So maybe there are local minima, but they seem to be typically all pretty, close to each other. And so maybe there's something in the structure of the optimization problem which makes it easier to learn. And so in this 2014 paper, what we studied is the effect of dimensionality, that as you consider higher dimensional parameter spaces, the local minima become closer to the global minimum. And the only critical points that you encounter on your path from initial parameters to convergence are saddle points. So if your optimization methods is robust to saddle points, then you're in business. And in fact, SGD is robust to saddle points. So that's, and then, more recently, there's a lot of work from learning theory people and optimization theory people about over-parameterized neural nets. So it's in the same spirit that if your neural net has enough degrees of freedom, then you're actually able to get essentially global minima or pretty close to global minima in terms of the training objective, of course, right? So what's also surprising is that this works even in terms of generalization performance. So today, the common wisdom is you want to use a network that's larger than necessary. And it will make the optimization easier. So you will typically get to zero training error. And somehow you still get good generalization. And I mean, my intuition as to why this works is pretty simple. So a large neural net, which has enough capacity to learn the function, the training set by heart, has more capacity than you need. But what happens is, as you train, you kind of use that capacity a little bit at a time. With SGD, you can't go directly from a simple function to a complicated function. You go through a series of steps in which you make the function gradually more complex. And as soon as you hit zero training error, it stops. You don't go beyond what is necessary to get training error. And then there's the SGD aspect, which somehow regularizes the whole thing. So even if you had an infinite capacity neural net, it wouldn't overfit. Just like, think about a kernel machine. In principle, it's like if it had infinite capacity, if you have a kernel like a Gaussian kernel, but it doesn't use more capacity than the number of examples. So there's something similar going on. And of course, there's a lot of interesting work in that space these days that tries to exploit specifics of the architecture of neural nets to explain why we're getting good generalization and easy optimization. It's not always true. So there are still problems where optimization is hard. But for the most part, like object recognition, optimization is a piece of cake. Noise in the parameters could be injected, for example, in dropout, is a way to help both optimization and generalization. So one insight that I really love about this is if instead of considering the parameters theta and the cost for the parameters theta as the thing you want to optimize, you take your theta and you add a bit of noise. And then at each optimization step, you consider a different theta around your current theta, like different noise, basically. What you're optimizing is this convolution of the original objective function with a Gaussian. And that's going to smooth that objective function. And smoothing the objective function is going to get rid of bad local minima that are not very deep, but very thin. And it's going to make optimization easier because now, just following the gradient is going to be easier. You don't get trapped in like stupid, complicated meanders. And so adding any kind of noise in the operation, which you get by SGD, by the way, but also dropout or other methods, is going to have this regularization effect, which helps both optimization and generalization. So this is like a picture to understand what is going on. If you have a lot of noise, if you smooth the objective function a lot, then it's convex. At some level, it has to become convex. And so finding a minimum is easy, but of course it's not the minimum you want. But now if you reduce the amount of noise, which you can get in various ways, like decrease the learning rate, just does that for SGD. Then you're now optimizing something a bit different, which is a less smooth version, but you start from a really good place. And so you can track the local minima as the objective function is changing. This is called annealing or simulated annealing or continuation methods. And I think it's an interesting way to think about how we can make a difficult nonlinear optimization problem easier. And one of the approaches that's related to this that I worked on is called curriculum learning. And the idea is that you don't take the training data as IID and then just present them in some random order. You start with the easy examples and you gradually introduce more difficult ones or more difficult tasks. And if you think about how humans and animals learn, the reason it's called curriculum is because that's the way we train animals, for example. This is the way we train children. We don't take a 6-year-old to university. We first teach her simple things that she can grasp, and then we build on top of the concepts that she has already learned. Right? So this is something that is very, very useful in reinforcement learning, where the optimization problem is harder, much harder than in standard deep learning, and where often doing a curriculum approach really solves the problem. But the issue is we don't know how to design a curriculum. Okay. And similarly, you can do pre-training. So you can say, oh, I'm going to break my task into the composition of two tasks. I'm going to first learn how to map my input to some intermediate targets, and then how to map those targets to the things that I really want to predict. And then I can do fine-tuning of the whole thing end to end. And that usually helps a lot as well. How do we debug neural nets? These are complicated machines. You can have a neural net that seems to work, but actually there's a bug because it may well look good, reasonable, but you could do a lot better. And so there's an art to how to debug these neural nets. First of all, you have to make sure you can make your experiments reproducible, because if you're always like in a noisy environment, it's hard to know the effect of a change. You want to make sure your gradients are correct. Well, these days you don't need to worry about this. One simple way to make sure that the optimization works is to train on a small data set and verify you can reach zero training error quickly. If you don't, then there's a bug or something wrong in the setting of your hyperparameters, like your learning rate is too large or something. Then you want to monitor a lot of things while you're training. You want to monitor error curves. You want to monitor interesting statistics of the weights, the gradients, and so on. And there's much more that could be said. You want to vary capacity, like the size of the net, the number of parameters, and observe how it gets you to more overfitting or more underfitting. You want to compare with simple models like logistic regression, kernel machines, random forests, that you have code that works, and you want to make sure that you at least do as well, or if you don't, you want to understand why. You want to track not just one metric, but many metrics, just in case there's a bug in one of them. You can, now this is more intense, but you want to look at examples on which your predictor is making mistakes and try to figure out why it is. You want to change the number of training examples and see if you get what you expect. And you want to make sure you have enough test examples to be able to compare methods and conclude with good statistical significance. All right. Let me now go through a few architectures, convnets and recurrent nets. Let me see how I stand with time.
Joshua, do you think maybe you have time now to answer some questions? There are some questions.
Yes, perfectly. Let's do that. Good time.
So Sashit, can you unmute yourself and ask the question?
Yes. Hi.
Hey.
So you very briefly mentioned pre-training here.
Yes.
And so I was wondering what you think at a high level of Dr. LeCun has this cake analogy that he likes a lot with the unsupervised or self-supervised stuff as the bulk of it and stuff. I was wondering what you think of that and what you think of the future of pre-training things or doing like unsupervised pre-training and that kind of thing.
Yeah, sure. Well, I mean, for the cake analogy, in terms of number of bits of information, it's totally correct. In terms of what the problem we have to solve, ultimately, it's the reinforcement learning problem, right? I mean, like we can't label everything in the world. And it's not going to be enough to use the rewards to train that. So we're going to need the huge number of bits of information we're getting by unsupervised learning or self-supervised learning or whatever. Okay, so that's my cake take, but basically, so I basically agree with Jan, except that I think it should not be understood as like RL is not important, but rather it's hard. Yeah, pre-training. Well, I mean, pretty much all of the state of the art in NLP these days is obtained by pre-training. So it's been amazingly successful from that point of view. You train on large corpora the representations of words and phrases, and then you can just fine-tune a few extra parameters for your task depending on how much data you have. And there are many ways of doing this, and it's a heuristic, but it's one that works well. I prefer the scenario where you define one objective function, which may include some unsupervised learning terms and some supervised learning terms and maybe some RL terms, and you just train with respect to that, right? And some example only give you unsupervised information, and others give you rewards, and others give you labels, whatever. So I prefer to think of it like this.
Cool, thank you.
Any other?
So yeah, there are some questions, but maybe, I don't know, maybe if you want to continue, yeah, because people's not raising their hands, so.
Yeah, okay. Yeah. So let's talk about convnets. And I'm not going to spend a lot of time on convnets. I guess is someone talking about computer vision? So I'm sure they'll talk about convnets, right? But I'm going to stay very abstract. Replace matrix multiplication by convolution. Convolution is a linear operator. What's nice about it is the same, very few parameters allow me to specify that a linear operator, which if I had to represent it as a matrix multiplication, that matrix would have a huge number of parameters. So it's going to allow us to do things efficiently from a parameterization point of view and also from a computation point of view, because that matrix is full of zeros. So that's the basic heart of it. And I'm going to go a little bit deeper. But otherwise, it's just like other neural nets. We can train them with whatever objective function we like some likelihood in supervised learning case. We can use backprop to compute gradients and so on. And so, so convnets have been designed initially for images, but actually before Jan did his convnets for images, I think the first paper was 1989, there were something very much like convnets that had been proposed in Jeff Hinton's group for time series, right? So for sequences, you can do 1D convolutions, and those were called time delay neural nets. Very, very similar to convolutional neural nets, except in 1D. And there's this idea that really, I think Jan has pushed, but came from also the work on the neocognitron by Fukushima, of having a hierarchy at different spatial scales, right? So you can introduce between the convolutional layers, you can introduce these pooling layers, which reduce the spatial resolution. And thus, as you go higher up, you get like these smaller images that have less spatial resolutions, but now each feature is about a larger part of the input, and thus can be capturing something more abstract. And so you create this multi-scale hierarchy where you have just a few features at each position, the same features at all the positions in the early layers. And then as you go downstream of that convnet, you're going to have few positions, but many more features. Right? So there's a less spatial resolution as you go up, but more features as you go up. And that was part of his initial design in 1989. You can play all kinds of games with convnets. Like neural nets in general, you can combine many sources, you can fuse them, you can take the representations that you got from one path and just concatenate it with the representation you get from another path, and that becomes the input for follow-up processing. Yeah, so that's all I'm going to say about convnets. I'm sure you'll see more elsewhere. I'm going to spend a bit more time on recurrent nets. One reason being I worked a lot on recurrent nets, especially in the 90s. And I still work on them. And recurrent nets are, directly inspired by the brain, because your brain is a big recurrent net. What does that mean? It means it's not a feed-forward thing. Computation isn't done in one go. There are feedback connections. So the whole thing has dynamics. If you stick in an input to your brain, it continues. If you keep the input fixed, it continues processing and trying to make sense of it through iterations of computations where both feed-forward connections and feedback connections interact in some dynamics. And so you can represent that by having those like feedback connections, like the W here, that go from higher up in the hierarchy to lower in the hierarchy. And now, in order to think about this from an optimization perspective and thinking about it like logically, how are we going to train these things? very important notion is the idea that, well, we should look at the sequence of computation. So if we do it in discrete time, you can also do it in continuous time. A lot of the early work was in continuous time, but it's more convenient for a computer scientist to do it in discrete time. And at the end, even continuous time, people discretize time because they have to do simulations. So if you do it in discrete time, you can see at each instant, the values of the hidden units is going to be different from the previous instant. And so really, I should think of this graph of computations, right? So this is called unfolding the recurrent net into this flow graph, where now the hidden units is like there's a different instance of them at each time step. But the weights are going to be shared, right? Because the weights don't change that quickly. And so the same weights are going to be used at all those time steps. So that's like the basic structure of a recurrent net. It doesn't matter what exact computation you do, how many layers you have, it has this flavor of essentially a dynamical system with parameters and nonlinearities. So why is that even interesting? Well, recurrent nets have been used mostly to process sequences. And one problem with sequences is you can have sequences of different lengths in your data. They're not all of the same length. And usually sequences have some sort of stationary property, like the features, just like in convnets, the features that are good at a particular position in space are probably good if we were to compute the same feature at a different location. Similarly, in time, you want to extract the same feature at different times. And also you couldn't, like because there may be sequences of different lengths in your data. If I were to have a different function for every length and not share parameters between those functions, it would be very bad from a generalization perspective. But because of, again, properties of the world around us, like if you think about physics, it's the same laws of physics at each time step. What changes the state of the world, right? And that's why, in math and engineering, dynamical systems are so important. And so we want to exploit this temporal equivariance as well in machine learning. And so instead of learning functions like the GT here, which would be a different function for each length and would not necessarily take advantage of this kind of equivariance structure, we can learn a dynamical system like on the top, where we say we can learn a state variable as a parameterized function of the previous state variable and the current input. Now that's a very general pattern. You can make it as complex as you want, but a lot of architectures can fit into this. And the advantage with this is because the same parameters are used at every time step, you can now generalize to new lengths not seen during training. And you get this equivariance property, just like we had in convnets. So now you can use RNNs, various architectures of RNNs in many ways, but one that's interesting and related to what I talked about earlier using autoregressive probabilistic models is you can use them as generative models for sequences. So I talked about it for language earlier. And I said we used a fixed size input. But now if you have a recurrent net, you can make the state of the recurrent net a function of all the pasts. So I can truly represent the joint of a sequence as the product of conditionals of the tth element given all the elements up to t-1. So how would we do that? Well, we would have our recurrent net architecture, whatever it is, but then on the output, we would produce the parameters of a distribution. Remember, we're going to do this maximum likelihood stuff. So we're going to produce the parameters here, if it's words, of a multinually over all the words. So we have the probability for each possible words in a softmax. And then if we wanted to generate from that, well, we will just do ancestral sampling, meaning we're going to sample the first word according to some prior distribution, and then we're going to sample the second word given the first one, and then the third one given the first two. And we can do that because if I look at like the tth one, I have a distribution over its values given all the previous ones. Oh, sorry, this would be a distribution over the t+1 one. And then once I've sampled the word from that, I can just stick it in as input for the next computation and generate the distribution for the next word, and so on, right? So we can generate from it. We can also train by maximum likelihood. In other words, if I give you the sequence of words, I'm not going to copy the sample into the next input. I'm just going to use what is observed and compute its likelihood given its parents in the chain, in the previous words. And then that's going to be my training objective. So that's how you can use recurrent nets to generate any kind of sequence. And now that you understand that you can generate sequences, you can do, of course, conditional generation. So you can generate a sequence given another sequence, right? So map a sequence to another sequence. You can map a sequence to a vector. So you just read a sequence, now you have a state variable. This is the top right architecture. You read a sequence, now you have a state variable which summarizes all the past inputs. And then you stick that into your favorite, a neural net, and you've got a conditional distribution for some output variables. You can do sequence to sequence of the same length when they're aligned, but often you want to do sequence to sequence of different lengths and maybe different types. So this is the standard sequence to sequence architecture. You have the recurrent net, which reads the input sequence, produces a state representation of the whole thing, and that feeds the generative RNN, which can sample an output from the output distribution. Now notice the output is not a simple object anymore. It's not like a class. It's a sequence of symbols or a sequence of numbers or something. And so you have to represent its joint. And earlier I said, well, how do we represent the joint distribution over many variables, conditional on something? Well, here's a very simple tool for doing that, which uses the autoregressive trick. That's very old. Okay. So that way of training a conditional distribution or a generative model is also called teacher forcing, because when we train, we are taking the actual data at each point in the sequence, the YT here, as an input, whereas an input for producing the next thing. Whereas when we are sampling from the model at generation time, we don't take the data because we don't have the data. We take a sample from the conditional distribution of the data estimated by the model, and then we stick that as input. But there is no guarantee that the samples from the model follow the same distribution as the data. Of course, that's how you train it so that they match, but in general, they won't. And so the sequences you're going to get might be different in nature. You might veer off the training distribution, and then your generator can produce garbage because it gets into a place that doesn't look like anything it's seen during training. And this mismatch, is due to a sort of compounding error, or like a problem of out of distribution generalization in some sense. There are a number of papers that try to address this, but I don't think it's a completely solved problem. You can do all kinds of RNNs. You can, one of the oldest ideas to try to train them more easily is to use a hierarchy of different timescales. Oh yeah, I only have 2 minutes to talk about the problem of vanishing gradients. So I started working on this in the early 80s. And basically what happens is related to the dynamics of these recurrent nets, that if you start from some point, you might end up in some attractor. If you start from another point, you might end up in another attractor. And the thing is, if you vary the initial point just a little bit, you don't change where you end up because it is an attractor. And so the derivative of the final state with respect to the initial state will be 0, except if you're right sitting on the boundary, and then it's going to be infinite. And so you get either vanishing gradients or 0 gradients, and both, or infinite gradients, and both are bad in various ways. And yeah, so the problem is, in order to have a recurrent net that is robustly storing information, even one bit of information, you need to have these attractors. And so you're going to get this vanishing gradient phenomenon. And what it does, as was actually first highlighted in the thesis of Sepp Hochreiter in 1991, is it's going to give you vanishing gradients for the long-term dependencies. And if you look at the gradient, the total gradient as a sum of gradients over different time spans, there's one factor here, Jacobian, which is gonna vanish for sequences or dependencies that are over long spans. All right, I'm gonna stop here and continue tomorrow and take more questions now. I don't know if there's time for that, but I am available.
Thanks a lot, Joshua, for your amazing talk. Yeah, so there are some questions. Yeah, for instance, like, do you think that artificial general intelligence will be achieved with neural networks, or it's more likely that you need other models?
Okay, so first of all, I don't believe that there is such a thing as artificial general intelligence, because the most intelligent entities that we know, human beings, don't have artificial general intelligence. Like, as in, like, we don't have a completely general intelligence. There are a lot of problems we're really bad at. So that's the first point. But if you mean whether we're going to reach human level intelligence, which is a term I prefer a lot more, yeah, there's no reason why we couldn't build machines that are going to be as intelligent as us, because our brain is a machine, right? And we just have to figure it out or find the principles and build machines accordingly. Whether it's going to be neural nets, of course it will, because our brain is a neural net, right? Now, maybe along the way, we understand the underlying abstractions that are going on, and then we're going to decide that we don't have to implement it as a neural net. Once we understand the principles, right, there are potentially many ways and potentially some more efficient ways of implementing things. So I don't have a crystal ball, but yeah.
So there are two other people that want to ask questions. You can unmute your microphones and ask.
Who goes first?
Let me.
You can go first, yeah.
Right. Thank you. Thank you very much. Thanks for the talk. I'd like to go back to the curriculum learning real quick.
Sure.
I find that super interesting. And I feel that in generative models, so when you think of the progressive growing, you know, these GANs from Karas and colleagues at NVIDIA, I think they do that when they start with the super low res versions and then scale them up.
Yeah.
So it seems to work really well in there. And then when I look at non-generative learning, more classical problems, I wonder, I think I should be seeing that everywhere. Maybe just in a hierarchy, for example, when you learn on ImageNet, maybe understand what are dogs versus cats first, and then get into all those different breeds of dogs.
Right.
Really, that isn't done.
So the problem is we don't have a general recipe for doing curriculum learning, and there are some papers that try to do that, and I don't want to decrease their value, but I think it's still an open problem how to automate the construction of the curriculum. And if you look at how humans do it, it's not like there's no recipe either. There's a lot of experience of teachers and generations of like curricula that have worked. And so learning a good curriculum is itself like kind of a meta learning problem that we have to grapple with.
So it's just, you think that the problem is just so very hard, and that's why we don't see more of it?
I think it's because it's more like a meta learning problem. It's like there's an outer loop, there's an inner loop, which is training an individual, educating an individual, right? But there's an outer loop, which is designing the curriculum. And until we, deal with it in that way, I don't think we're going to get anywhere. But that, of course, is going to take more computational resources. But as we get more computational resources, I think this will become the direction for curriculum learning. We can also use human curriculum, right? And if we make progress on natural language understanding and a kind of representations of high-level concepts that I'll talk about tomorrow, then we might just be able to write on the curricula we use for humans, children.
All right, thanks. Thank you very much.
Abjit had also a question.
Yeah, hi. Thanks for the great talk. I just wanted to ask about the overparameterization that you talked about.
Yes.
And you suggested that SGD might be helping in regularizing and slowly moving towards a global optimum rather than overfitting or something. Yeah. I wonder how that relates with the lottery ticket hypothesis, and what's your take on that? That it's basically just an overparameterization could help, a model get a lot more lottery tickets, and then it's easier to win the lottery.
Yeah, I don't think it's a sufficient explanation, because this is a very high dimensional space, and so there's a lot of tickets. And SGD, with all the noise and all, does explore more than like a straight gradient descent, but it still couldn't go exponential in the number of tickets, and so I think there is more to it.
And Pedro.
Hi. Yeah, thank you for the great talk. So I was wondering, you were mentioning the brain as a neural network. So one of the issues that deep learning has, and I guess it's one of the reasons why it's not able to generalize for out of distributions, is the requirement that the data has to be IID. And I would imagine that that is something that our brain processing system does not require. So how can you address this limitation, and what type of work is it being done?
Most of my lecture tomorrow will be about this.
Okay, great.
Actually, I think we can leave the rest of the questions for the roundtable. Thanks again, Joshua, for the nice talk.
My pleasure.
Thank you.
Thank you.
We're gonna meet at 4 o'clock for the roundtable with Yoshua.
Bye.
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 Thank you. Bye-bye.